have to do it for you. You just have to tell me next slide. So thank you so much, everyone, for your patience. I'm Barry Cooper from the organising committee, and on behalf of them, we're delighted to have Yang-Hui He come and talk to us about AI-assisted theoretical discovery.
When should he finish this work?
Yeah, thank you very much for this kind invitation. I really apologize for all the mess up. It took me 30 minutes to install Teams Classic and reinstall Teams to get this working. So let me just next slide, please. So I'm gonna try to talk about. I know what I'm talking about is slightly off topic because this is mainly about theorem provers, but I will actually mainly focus on the second and the third directions in this review that I recently wrote. So it's actually timed quite well because of the three parts of how one actually does mathematics. What I try to term as bottom up, top down, and meta mathematics. I can skip the entirety of part one, which is exactly this. What this conference is about, and you can hear from all the experts like Demora and Kevin, who are friends of mine. So we can skip to. Let's go to next slide. Next slide. Next slide. We can keep on going until we move to the second part. So next slide. Next slide. Yeah. So let me just start from top-down mathematics, which is not about theorem proving and how it complements theorem proving in terms of discovery. You can think about AI theorem provers as finding a pathway towards a proof, and experimental mathematics is what one thinks about how one can find a pathway towards discovering a problem to prove. So next slide, please. So this is very much in the spirit of what Arnold said about what mathematics is. That mathematics is a branch of physics where the experiments are super cheap. And recently, the theoretical physicist Mike Douglas have called mathematical data Platonic in the sense that it is a pure data free from statistical error. There could be mistakes in it, but it is at least from statistical fluctuations in experimental data. So how does one formulate problems and conjectures from available mathematical data? Next slide, please. So perhaps the most famous example of this kind of mathematical discovery goes back to 19th century Gauss. And one could argue that Gauss was the greatest neural network of the 19th century. So Gauss was able to look at and plot the number of primes less than or equal to a real positive number x, and then he was able to conclude by inventing statistics that this is roughly x over log x. This is probably one of the highlights of mathematical experimentation, because the proof of this had to wait for 50 years, when complex analysis was rich enough to be able to prove something like this. And in the 20th century, the BSD conjecture was very much also in this spirit. I mean, BSD conjecture started in the 1960s when Burton, Swinton, Dyer, in the 1960s, they hid in the basement of Cambridge and used the EDSAC computer to discover this pattern that relates ranks to conductors of elliptic curves. In fact, one should emphasize that 1/3 of the remaining Millennium Prize problems actually came from just mining data. Right? So it's very natural that in the age of AI, that mining data could be an assistant to fundamental discovery. So next slide, please. So some of the early experiments, because my background is in mathematical physics and algebraic geometry, some of the earliest experiments that I was doing was just to feed in Clavial data that I had available. And the details are not important, but if you represent a Clavial manifold, in fact, any algebraic variety, and then just do a supervised machine learning of computing its Hodge numbers, that was a very natural thing to do, and that was the kind of thing that I did back in 2017. And then one way to do it is just to pixelate a variety, and then just do this as if it were a handwritten recognition problem. So then he kind of became a fanatic in this way, and then tried to argue that maybe any problem in algebraic geometry can be pixelated in this way. So next slide, please. So I'm very grateful to, to all of the collaborators and friends and my very talented students and postdocs for all the help in just teaching me different Platonic data from different fields of mathematics that one can mine using machine learning and data theoretic techniques. In some sense, this goes under the rubric of AI-assisted discovery these days. So I can skip the next slide. And the next one. Yeah, so here's an interesting plot. If you look at the number of papers on the archive whose abstract and title that mention words such as machine learning, AI, data science in the past 80 years or so, you can see in fields that are unlikely to have such words. You can see this is a very rapidly growing field. And of course, this is a gross undercount because, I only tried few words like machine learning, neural network. And if you included all the possible keywords that are kind of AI related or language model, the curves would be much, much bigger. And I really should redo this curve at some point. But as of December of 2025, this will look like. And it's interesting, the most number of papers in the field that studies this kind of stuff is GRQC, or quantum gravity and general relativity. The reason for that is because these guys use a lot of numerical computations for metrics, and that is very likely to use this kind of technology. And it's very reassuring to see very pure fields like number theory, algebraic geometry, and representation theory also growing in the number of papers that at least use deep learning techniques. Next slide, please. And if you can see the number of AI for Math annual series that have gone since then, it's been quite exciting. Here's an overview. So like the string theorists were probably the first ones to pick up. So there's been an annual conference since then called String Data that kind of does this stuff. And more recently, there's one on AI for Math in Singapore that was launched in 2025. And in 2026, our institute has launched a series for AI for Math discovery. So I think it's very timely that this conference in Exeter is, I hope that it would also become an annual series. And next slide, please. So given all of this, and I think if Kevin is in the audience, he may appreciate this, because back in 2024, we had a conference together, and at Cambridge, and the title was very, very broad. It basically included everything, and the word machine learning should also have been in there, but it didn't fit the number of characters that we were allowed. So basically, it was everything, including the kitchen sink. And those are the big conference was mainly just to bring anybody who was interested in this kind of exploration together. And there we were listening to an online talk by Birch himself, and with Kevin and friends, we tried to say that, well, given this kind of AI exploration in Platonic data, there should be a more stringent test than the fact that ChatGPT passed the Turing test in 2022. So it was very appropriate that we named the test after Birch. And it's again, like the Turing test, the Birch test is not a well-defined test. It's just like a basic gut feeling. Unlike the ARC test, the ARC test for artificial general intelligence, which is an actual list of puzzles which an AGI has to solve. The ARC test is much more precise than both the Turing test and the Birch test. So, but basically, the Birch test vaguely goes under AIN for AI, where next slide, where A is for automaticity in the sense that this discovery has to be automated by AI. And the next slide. I has to be interpretable and has to be concrete enough to be conjecture. So the early experiments that I was doing and a few other people in mathematical physics were doing were not interpretable. Just because you find a deep neural network that can compute Hodge numbers doesn't mean that it's of any use to mathematics. It's of use to physics because it could compute things very fast, and that often gives you a very quick a quick estimate to the number of a physical quantity that you need. And the next one is n, which is non-triviality. You can imagine if you start data mining in this thing, a machine learning algorithm can discover all kinds of conjectures, and you can probably generate millions and billions of conjectures per second. But which ones are actually interesting? And so that's, we call that the N test. So next slide. And the most important thing, of course, you actually have to make Birch happy. I think, Birch, a genuine AI discovery would actually, I think, would make, hopefully, Birch very happy. So next slide, please. So there have been examples that have been close to the Birch test. In 2022, there was this beautiful paper that I wasn't involved in. This was a paper of Davis et al. In DeepMind, and with Jody Williamson and friends. What they did was to use saliency test, which is a standard technology in machine learning, to kind of map the of that are related to the Jones polynomial, based on the snappy data set of 3.5 million knots. And they were able to use the saliency test, extract out the ones that are likely to be related to each other, and then actually conclude a new formula in the Jones polynomial. So this was a very beautiful work. And then, this in some sense it passed the A test. It was an automatic, saliency is an automatic thing to do. The I test was passed because it was an interpretable formula, but it failed the N test because they were able to prove this formula themselves. And in the same year, there was this paper that I was writing with number theorists Lee, Oliver, and Poznikov. This was very interesting. By data mining elliptic curve data, which was 3.5 million elliptic curves, where we chose to do about 100,000 of them, but we were able to extract a relation in the Euler coefficients or the trace of Frobenius in the L function. And it failed the A test because we were mucking around. I'll say a little bit more about the memorization conjectures in a minute. It failed the A test. It passed the I test because there was an actual formula you can give to mathematicians, and I think that was for the first time it actually passed the N test. This is still an open conjecture. The general memorization phenomenon has features that we now believe to be true for all our functions. And this was very nice because it's still an open problem after 4 years, and people and actual number theorists. There's a community of number theorists actually working on this. So that was very that was kind of cool and very exciting for me. And then we're getting, of course, it's only a matter of time before we completely pass the Birch test, right? In 2025, DeepMind's collaborations, they were discovering singularities. In 2026, just in the last 3 months, various AI companies like Aristotle, Harmonic, DeepMind were solving genuine problems. Even though the numbers that you read in the newspaper coverage is always a bit higher than it actually is, but there are genuine new problems solved. For example, 13 of the 700 problems of the Erdős problems are, I believe, genuinely believed to the mathematical community to be solved. Of the 67 problems that were proposed to AlphaEvolve by Tao and collaborators, 23 have been made genuine progress. Axiom AI has solved 4 small open problems, and probably the most interesting one is the one that was given in February this year, where Martin Harrow, the Fields medalist, gave 10 problems, you know, of research level, and Gemini and also OpenAI actually solved 6 of them by peer review. And I think there have been 2 more. I've just learned this on Monday. There's a Chinese company called Reflas, headed by Don Bing and friends, and they actually solved 2 more of these first proof problems. So this is now, I think, it's only a matter of time when we, however defined, that we will pass the Birch test in terms of a genuine mathematical discovery. Next slide, please. So I think I'm gonna so yeah, if you click on the top of the little blurb that says memorization conjectures, yeah, this should bring you to this to the memorization conjecture. And I think you can probably skip this slide because this was just a slide on it's a quick introduction what the BSD conjecture is, and you can probably skip this to the next slide. So the memorization conjecture. So let's in essence, the weak Birch-Swinton-Dyer conjecture is that given an elliptic curve, show that its order of vanishing of its L function is equal to the rank of the elliptic curve. So if you can prove that, you already get $1 million. If you can prove the stronger one, you'll get liked even more. So if you go to the next slide, please. So what we did was there's an interesting backstory to this. Because my background is in algebraic geometry, if you give him an elliptic curve, the first thing I would do is to do the Tate or the Weierstrass representation of the elliptic curve, namely, something like y squared is equal to x cubed plus a bunch of coefficients. So back in 2018, I was already trying to think, because I was having so much luck with computing Hodge numbers from algebraic varieties by feeding to deep neural networks. I was trying something whether I could actually predict the rank of an elliptic curve by looking at the coefficients of the Weierstrass function. And of course, I failed miserably, because the Weierstrass representation of the elliptic curve doesn't, under any level, contain the deep arithmetic of the elliptic curve, where the BSD conjecture is all concentrated. So that's really interesting, right? So in some sense, had I been lucky to have discovered something like the memorization by myself, that would have passed the A test. But I actually had to talk to experts, actual number theorists, and I'm not a number theorist. So that's in essence that immediately deletes this discovery as an automated discovery. So, but it was fine. I was giving talks about finding Hodge numbers by looking at coefficients in an algebraic variety, such as an elliptic curve, and Lee and Oliver happened to be the audience. This was back in, I think, in 2021, and even earlier, 2020. And they said, well, they gave me the key insight, which was, well, you shouldn't be looking at Weierstrass coefficients. You should be looking at Euler coefficients, which is trace Frobenius in the L function. So precisely because they're number theorists. So then you try to predict rank by looking at coefficients, even 50 coefficients. If you take the first 50 primes, you would 0% accuracy in prediction already went very quickly to 99%. It didn't surprise them, because they said, well, basically the BSD conjecture was working under the hood to make such a prediction possible. How exactly it was doing it, we had no idea, because you feed into some neural network, it wasn't very interpretable. So here's the interesting bit. Because we were teaming up, the better thing to look at was to see, well, since it was so good at predicting rank, well, let's try different algorithms. Let's try, principal component analysis. That seemed like a good thing to do. So once you do the PCA, and PCA is very visual, right? PCA just basically projects high-dimensional data to, say, 2 dimensions, and then you can look at it. So now here's a plot of about 50K random elliptic curves, but each of which have been taken a list of its Euler coefficients. It's very hard to visualize that in 50 dimension when you take the first 50 primes or 100 primes or 100 dimension. But if you do PCA, it projects down. It looks like this. So this is very nice because PCA is a linear transformation that takes essentially there are 100 by 2 matrices, right? You're projecting 100 primes down to 2. And it looks like this. So, and then it's separated ranks 0, 1, and 2, which dominated over the space of elliptic curves. It's certainly over the LMFDB database. So this is interesting. You can actually look at these matrices. By looking at these matrices, and if you go to the next slides, and the guy who did it was Pozniakov, who was a student, who was just a second-year student at the time. He was able to, well, this is the kind of thing you give to students to do. You don't want to look at, 100,000 matrices. But he was able to take a big sample and actually looked at it. And by looking at it, he saw that the matrices were the non-zero interests of these matrices were focused on just essentially a single column. What that means is that all the PCA doing is an average, and so now we can extract out a precise formula. So this is the vertical average. So what you do is you fix a prime, but you average over all elliptic curves within a conductor range. So that's a formula, and you can take this formula. So we took this formula, we wrote to Peter Sanak, who's the and then who was the leading number theorist, and also and Sutherland, who developed the LMFDB, and asked them whether they've seen before. Didn't, and that was a bit surprising. And Sanak said this is quite shocking because this average should have been done by Birch, Swint, and Dye, but they didn't. And in some sense, we were not surprised they didn't do it because BSD were not thinking in terms of machine learning algorithms such as PCA. So once you do this average, it plots like this, and that's where the word enumeration comes from. So each color is a different rank of the elliptic curve. So now there are a lot of people working on this field, and once you take the infinite limit to the space of all elliptic curves, these actually converge to precise curves, and then these curves should fundamentally tell you what is the bias within the rank of how to decide what the elliptic curves are in terms of this. So this is a new phenomenon that people are still working on, which is kind of assuring. If you go to the next slide, please, and next slide. And then if you click that bubble, so yeah, so here, so in this sense, not only do you need to choose the right representation of the elliptic curves, but also you need the right features to be able to extract such a thing. But I highly encourage people in the audience to please look at about a terabyte of free mathematical platonic data online. If you want to look in group theory, go to GAP. If you want to go into algebraic geometry, go to GRDB and CLABIAL databases. If you want to go into number theory, LFDB. On knot theory, it's snappy. So these things are growing, and the entire internet is far bigger than this. And we should read in this about terabyte of data and start doing. I mean, this really is kind of automated as a machine guided discovery. So if you want to call this AI, at some level, I guess you could. So if you could just skip the next one. 2, keep going, yeah, to this now, yeah. So this conference is about formalizing what I said in what I focused on talking about is about finding a discovery process. And so, both of which, this top-down and bottom-up approach are I believe, important in how AI can assist us. The third direction of doing mathematical discovery is one might call it meta mathematics, or just simply large language models or math. this is a very mysterious direction on how math could be done. If you don't have verifiers, or if you don't formalize things into lean, LLMs is going to say all kinds of hallucinations that are just simply wrong. And yet, even without the ability to auto-formalize everything, it's quite remarkable how far LLMs have proceeded in making genuine contributions to mathematics. So if you see on the next slide, this is a very rapid progress in the last 4 years or so, right? In 2022, I mentioned ChatGPT passed the Turing test, which also happened to be the DeepMind paper on Jones polynomials and the memorization conjecture thing. And in 2023, there's FunSearch. 2024, AlphaGeo. 24 to 25 has been now. Here is a transition level, right? So here, starting in 2024, we suddenly start having lean being incorporated into AlphaProof with DeepMind, and then once you start starting to incorporate in MATLAB, then this is becoming seriously reliable. As I mentioned, the last 3 months, Axiom and AI, Harmonic, Math Inc., DeepMind, and RETHLAS are all incorporating lean into the language models in terms of trying to solving these problems. And this, I believe, is really the future of where mathematics is going. In terms of verifiable language models that can translate to MATLAB. And this will truly be the breakthroughs in terms of where mathematics is going. If you go to the next slide, please. So the joke is, in 2020, as of July of 2025, AI is approximately equal to the 12-year-old Terence Tao. That's because you can get a gold medal in the IMO problems. And if you want to do serious mathematical research, and that was immediately proposed around about the same time, if you go to the next slide. Frontier Math was launched by Epoch AI, which was funded by OpenAI. What if you give it real 2% advanced problems, right? So the idea is that we want to reach the 16-year-old Terence Tao as quickly as possible. So as of December 24, only 2% of advanced problems were solved by Frontier Math. And I'm going to give you an example of what the kind of frontier math problems are like. So if you think about this, so if you think of sort of three levels, right? You have the IMO benchmark. That's high school, really hard reasoning high school level problems. The frontier math are problems that have exact numerical answer. There's a total of about 500 of such problems. And the next level is the first proof, where you propose problems where you can actually humanly evaluate its proofs, but it's essentially peer review if you wish. So I was involved in frontier math level 4. If you go see the next slide, and as well as the next slide. And there, in fact, 30 of us flew to the Berkeley HQ of Frontier Math to try to come up problems to try to break the system. It was kind of an interesting story because Ken Ono, who is a very distinguished number theorist, was on one of us, and he was the most excited among all of us in terms of giving these problems and see it being solved. And to perhaps the surprise of the field, shortly after this experience, Ken Ono resigned his professorship from the University of Virginia, and now he's working full-time for Axiom Math. This is just to show you how excited the mathematics community is in response of LLMs solving problems in math. On the next page, you can see I believe this is Ken Ono's problem, and I believe this problem had been solved by several of the language models. I mean, just ChatGPT. This is nothing fancy, right? If you take this problem and you just feed into ChatGPT, and it will give you this answer, which there's no way it will just guess and hallucinate to get the right answer. So this is quite impressive. And if you go to the next, if you go to the next page. Oh yeah. So anyway, just to mention that at this level, about 10% of the problems that you saw in the previous slide can be solved by just LLMs that come out of the box. So these are ones that's uncoupled with lean. It's not axiomath, it's not harmonic. So 10% of math problems at research level can be just kind of guessed by just kind of by guesswork. And the reason is this is kind of cute why this is happening. We all taught the standard methods proof, right? Proof by contradiction, induction, syllogism, the standard things we're taught in school. But if you go to the next bullet point, there's a lot of the practical mathematician actually solves by many other methods, right? There's proof by intimidation, authority, citation, confusion, the kind of techniques professors use on their students all the time. And all of such methods have now gone under the general name of proof by vibe. And this is extremely important. This top-down mathematics is a lot of this is by vibing. There was a famous paper written by William Thurston, the Fields medalist, about the nature of proof back in 1990s, where he was trying to argue that mathematicians are thought to do everything bottom up. Well, he didn't use these words, but essentially by doing bottom up. But a lot of it is by intuition and by experience, which what one might call by top down. And these days, I think we would call them by vibing. And language models has done this vibing extremely well. So if you go to the next slide, I'll actually come to a conclusion now. So LLMs have learned the tricks of proof by citation and proof by authority and by proof by vibe extremely well. And this is why we're making such good progress, even without coupling to MathLib. So if you go to the next slide, you can skip the next slide. So basically, in summary, you can think about bottom up as a quote-unquote natural language processing problem. You can think about top-down mathematics as an image processing problem, and the LLM as this meta-mathematical way of linking these two directions. So if you go to the final slide, so one could imagine that the future of mathematics is where papers from the archive are fed to humans and AI together, where a top-down kind of vibing would formulate new problems from looking at the Platonic data. And then there will be an auto-formalization into MathLib. And then we'll find the proof pathway using some kind of reinforced learning environment to find such a pathway. And then it will be fed back to the human. Well, the human here is the 17-year-old Terence Tao, I think, where the essence of the proof will be digested, and then you'll be fed back to produce the paper. So I wrote this diagram about a year ago, and I thought, well, this is sometime in the quite distant future. But given that, if you move to the next slide, next slide. Given that even in the last 2 months, we've made so much progress in solving open problems. Of course, open problems have not so far, included major problems like Millennium Prize problems. But even in the last month, we made so much progress that perhaps one could argue that the future is actually now. So I think I'll stop here. And thank you very much. And I apologize for the big hiccup in the beginning.
Thank you very much, Regis. Okay, so we're happy to take questions in the question and answer chat if people want to drop them in. Just one from me in the room. You gave this example of mining data in order to try to understand conjectures, and so this is the future of mathematical research. Is this something you've also done with your students? It strikes me that is quite an exciting way of doing mathematics. Is this sort of experimental? Let's generate lots and lots of interesting mathematical objects, and see what emerges from that.
Yeah, absolutely. So yeah, in the big list was just asking asking my students and my and collaborators and myself, and we just try to generate a lot of data in addition to the one. So generating this data is so free right now. So for example, we were experimenting with quiver representations. So we generated a lot of quivers, and then try to see whether you could say something about general patterns in such quivers. Yeah, so I think this is a very fruitful and very cheap way to do things. This is a little more reliable than LLMs because there's no hallucination. This is, at the end of the day, we have to choose the machine learning algorithm and to try to interpret a pattern. And it's basically the neural net or in some neural network or AI is doing is to help us find patterns that we cannot visualize. So the memorization phenomenon was precisely one good example of this.
Thank you very much. Any other questions in the room or online? Okay. Well, it's a fascinating topic, and thank you so much for sharing your thoughts and experiments with us. And we'll just thank Yang-Hui He again.
Okay, and thank you. And